In the previous video, we talked about quantization and also discussed that quantization introduces error, which we call as quantization error. And we also went on to discuss and derive the expression for the average quantization noise power as a result of quantization. And we showed that the average quantization noise power turns out to be a function of the quantization step size delta. So it depends on the quantization step size delta, and therefore if we want to minimize the average quantization noise power, then we need to make the quantization step size delta as small as possible. However, doing so would result in increasing the number of quantization levels, and hence it will also increase the number of bits per sample. So that's the trade-off or the cost associated in if you want to minimize the quantization noise power. However, even though quantization introduces this noise and introduces quantization error, we still have to perform quantization because it would be impossible to represent the infinite possible amplitude levels, each with its unique binary combination. So therefore, we still perform quantization in a manner such that the quantization noise is kept as small as possible. That would not be perceived by the end user, depending on whatever signal that is being quantized. Another important fact regarding the quantization error and quantization noise is that it is non-reversible. That is, once the quantization error gets introduced into the signal, it cannot be removed. So therefore, it is imperative that the quantization error and hence the quantization noise is kept as small as possible. Just to give you an illustration of what that means, let's make the statement first. So quantization error and hence the quantization noise is non-reversible. That means once this error gets introduced into the signal, it cannot be removed. So therefore, we need to make this error or noise as small as possible. What do we mean by that? When we say that the quantization error is non-reversible. Suppose that we have these red dots representing our actual samples, and we quantize them to the nearest quantization level, as we have seen before in the previous lecture as well. So each of these is quantized to the nearest quantization level. Okay, so we'll just take a couple of the samples and see what we mean by the quantization error being non-reversible. So if you notice, the first two samples are both quantized to the voltage level 1 volt. So both the first two samples are quantized to 1 volt. Their actual values are somewhere around, say, the first one could be around somewhere 0.4, and the second one is around, say, 0.25. So we have the first sample approximately based on this picture, so it looks like 0.4. The second sample, let's say it is like something like 0.25, and these are the actual samples. Okay, these are the actual samples, and these get mapped to the quantized values. Now the quantized values in both these cases are 1. So let's say the 0.4 is mapped or quantized to 1 volt, and the 0.25 is also quantized to 1 volt. So both of these are getting quantized to 1 volt. And if we had to get back the original value from the quantized value, that means if we had to go back in the reverse direction to go from this 1 volt to the 0.4 volt. So suppose if the 0.4 and 0.25 were hidden from us, would it be possible to identify that this 1 volt came from 0.4 volt and this 1 volt came from 0.25 volt? It would not be possible to do that. So that is what we mean by when we say that the quantization error is non-reversible. So the actual sample here is 0.4, that got quantized to 1 volt, so that means there is an error of 0.6 volt in this case. And here the error is 0.75 volts. So the actual value is 0.4, that has got increased to 1 volt. So that's an error of 0.6. We cannot remove that error once it has got introduced, because once we hide these values, once the quantization has been done, the same quantized value could have been arrived at from different possible actual samples. So therefore it would be impossible to go back from the quantized value to the actual samples. So going back from the quantized value to the actual sample value is not possible. Okay, so not possible to go from quantized value to actual value. Hence we say that the quantization error and hence the quantization noise is non-reversible. That means once introduced, it cannot be removed. Therefore, it is important to keep the quantization error and hence the noise, the quantization noise, as low as possible. So how do we reduce the quantization noise? We discussed that in the previous video, where we said that to reduce, okay, if we have to reduce the quantization noise, so I'm marking a downward arrow, that means we want to reduce the quantization noise. In order to do so, we will have to make the step size delta smaller. Reducing the step size delta would mean the number of quantization levels, L, will go up, and if that goes up, then the number of bits per sample will go up, and that would mean more number of bits being produced per sample and hence per second, right? So the digitization process will end up producing more bits. We will need more bits to represent the signal if you want to reduce the quantization noise power. So that's a trade-off, and we will see later how to choose the value of L and hence the value of N in a practical scenario. We'll discuss about that later. Let us now focus on something much closer to the quantization itself, and that is, we've seen previously the quantization noise power NQ to be equal to delta squared by 12, the step size squared by 12. Now we'll see what is the signal to noise ratio. So we want to see what is the ratio of the signal power to the quantization noise power. And in this lecture, we will talk about two types of signal power. The first is the peak signal power, and that occurs when the signal voltage is at its peak. So if we have the peak signal amplitude, which is plus Vp or minus Vp, then we would have the peak signal power. So we will measure, we will calculate from this depiction, from this illustration here, what would be the peak signal power, and then compute the ratio of the peak signal power to the average quantization noise power. And later on, we will also compute the average signal power and then compute the average signal to average quantization noise power. So we are going to find two types of signal to noise ratios. One is the peak signal to quantization noise ratio, and the other is the average signal to the quantization noise power ratio. So we will compute each of them one by one. So what is the peak signal power? The peak signal power is the power of the signal when its amplitude is at its peak value. So when the amplitude reaches the positive peak or the negative peak, that's when you have the peak signal power. And we see here that we have considered a signal which has a peak to peak range going from minus Vp to plus Vp. So in this case, the peak signal power, which we are going to denote by the letter S subscript P, is going to be simply Sp equals, the relationship between power and amplitude is that power is the square of the amplitude. So that would simply be Vp square by R. So power is V square by R, voltage square by R. And for simplicity, we are going to consider R is equal to 1 ohm, normalize the resistor across which the power is going to be measured. So in that case, the power, the peak signal power, we can simply write that as Vp square. Now we can rewrite this signal power Vp square in terms of the peak to peak range. And if you notice from this illustration here, the peak to peak range, that is Vpp, is 2 times Vp. So if you notice here, Vpp is equal to 2 times Vp. So, and that is quite obvious from here, right? So Vpp is from the negative peak to the positive peak, and Vp is the distance from 0 to one of the peaks. So 0 to the positive peak, the distance is Vp, and 0 to the negative peak, the distance is also Vp, but in the opposite direction. So we have a minus in front. But the total distance from minus Vp to plus Vp, that is Vpp, that is going to be 2 times Vp. So that's 1 Vp and that's another Vp. So we can write the peak to peak range as 2 times Vp. And we can therefore, using this relationship, we can represent Vp in terms of the peak to peak voltage, Vpp, as Vpp by 2. So the peak voltage in one direction is nothing but half of the peak to peak range. So we can write that as Vpp. And why are we doing that? Because we are trying to represent the peak signal power in terms of the quantization step size delta. So we want to bring in delta into the equation, because if we can represent our signal power in terms of delta, then since we have from our earlier proof, from our earlier derivation where we had the quantization noise power as delta square by 12, so we can simplify that ratio when we compute the signal to noise ratio. So that's why we want to represent this signal power in terms of Vpp, because as you'll see now, we can now write Vpp in terms of delta. So just to give a quick idea on that, so let's see. The distance between the quantization levels is delta. So that distance here is delta, and that distance is again delta. That's another delta. That's another delta. And that's another delta. That's another delta. That's another delta, right? So if you see now, between these quantization levels, how many deltas are there? So that's 1 delta, 2 delta, 3, 4, 5, 6, 7. And each of these deltas is 2 volt in this example. From 5 to 7, that's 2 volt. From 3 to 5, that's 2 volt, right? And similarly, all these deltas are equal to 2 volt. And if you see here, from 7 to 8, that's 1 volt. So that corresponds to delta by 2. So this interval over here, okay, this interval over here, so that's a delta by 2. And similarly, at the bottom here, this interval from minus 7 to minus 8, that is another delta by 2. Now, the total range from minus 8 to plus 8, that is from minus Vp to plus Vp, which is nothing but Vpp, can be expressed in terms of delta. So how many deltas are there? That's 1, 2, 3, 4, 5, 6, 7, half here and half here. So that gives us a total of 8 deltas. And what is 8 in our example? 8 is the number of quantization levels. That's 1, 2, 3, 4, 5, 6, 7, 8. So it turns out that the peak-to-peak range can be written in terms of the quantization step size delta as VPP equals L times delta. So we can write VPP equals L times delta, and we are going to use this in our in representing the signal power in terms of delta. So we had, so I'm just going to draw a line here to continue this proof. So we had our signal power, which is Vp square, and we can write that as VPP by 2 the whole squared from this relationship. And then since VPP is equal to L delta, we can write that as L delta by 2 the whole square. So that would give us L squared delta square by 4. So the peak signal power can be written in terms of the quantization step size delta as L square delta square by 4. And we had previously computed the average quantization noise power, which we denoted as NQ, and we obtained that as delta square by 12. And now we are interested in finding the signal to noise ratio, the ratio of the peak signal power to the quantization noise power. So we take this ratio, so we call this as peak signal to average quantization noise power ratio, and we can simply denote that as SP by NQ. So what would that be? SP by NQ is simply L square delta square by 4 divided by delta square by 12, which we can write as L square delta square by 4 into 12 by delta square. So we'll end up with simply 3L square, right? The delta square in the numerator and denominator will cancel out. 4 goes here 3 times, so we end up with 3L square. So we see that the peak signal to average quantization noise power ratio is equal to 3 times L square, where L is the number of quantization levels. Now, in terms of the signal to noise ratio, we want to have the signal power to be as strong as possible, the noise power to be as low as possible. So that means the signal to noise ratio should be as high as possible. So we want the signal to be much stronger than the noise. So if the signal is strong, that means the numerator is large and the denominator is small, then this ratio should be large. So if you want this ratio to be large, then obviously we need to keep the number of levels. We need to increase the number of quantization levels. So L has to be increased. If the number of quantization levels is increased, instead of 8, if we make it say 16, then what happens as a consequence is that the quantization step size delta goes down, and if delta goes down, NQ will decrease. Okay, so for the same signal power, if we increase the number of quantization levels, the step size delta will decrease, and therefore the quantization noise power will also decrease. Then therefore the signal to noise ratio will go up. So in order to increase the signal to noise ratio, we need to increase the value of L. So that's the expression for the peak signal to average quantization noise ratio, right? The next thing we are going to do is, rather than using the peak signal power, we are going to use the average signal power. So in this case, the peak signal power is when the signal amplitude is at its peak value. But if you notice here, the signal amplitude is not at the peak value all the time. So the peak value occurs only very infrequently. So we are more interested in the average signal to quantization noise power. So we will measure or we'll compute the average signal power in a similar way as we computed the average quantization noise power. So we are going to make a simplifying assumption in doing so while making this calculation, and that assumption would be to consider that the signal amplitude is uniformly distributed in this peak-to-peak range. So we will consider that the signal amplitude is uniformly distributed from minus Vp to plus Vp, and then in a similar fashion as we computed the quantization noise power, we will compute the signal power here, and then we will take the ratio of the average signal power to the average quantization noise power. So to compute the average signal power, we are going to consider that the signal amplitude is uniformly distributed in the peak-to-peak range from minus Vp to plus Vp. The signal amplitude is having a uniform distribution. So we'll consider that signal amplitude is uniformly distributed in the range minus Vp to plus Vp. And with that information, we can now compute the average signal power as SA to be equal to the power is proportional to the square of the amplitude. So at any given time, the signal is having some amplitude, which we'll call as V volt. So the power is going to be proportional to the voltage at any instant. So if that voltage is V, we'll call it as V square. And the power will be V square only when the voltage is V. So we have to multiply that with the probability that the voltage is V at that instant and integrate it over the entire range of that the voltage value can take. So the voltage can go from minus Vp to plus Vp. So by integrating in that range, using the probability distribution of the amplitude values, we can compute the average signal power. And since we have considered that the amplitude or voltage is going to be uniformly distributed in the peak-to-peak range, then for the uniform distribution, we can write the probability distribution as, so for uniform distribution, P of V, let me write that a bit clearer. P of V is 1 by upper limit minus the lower limit. So the upper limit is Vp minus the lower limit is minus Vp. So that gives us 1 upon 2 Vp. So that's our probability distribution for the signal amplitude. And we can substitute that into the equation for the average signal power and then compute the integration. So therefore we can write SA to be integral minus Vp to plus Vp V square. P of V is 1 by 2 V capital, that's capital Vp dV. And since this capital Vp is a fixed constant, we can take it out of the integral. So that would give us 1 upon 2 Vp integral from minus Vp to plus Vp V square dV, and that would be 1 upon 2 Vp. The integral of V square would be V cube by 3 in the limit minus Vp to plus Vp. Okay, so we're just going to now apply the limits and simplify this expression. So that would give us 1 upon 2 Vp, and that would be Vp cube by 3 minus Vp cube. So that would give us minus Vp cube by 3, and that would evaluate to 1 upon 2 Vp into, so that would be 2 Vp cube, minus of minus would become plus, so that would become 2 Vp cube by 3. So that's going to give us the 2 and 2 will cancel, this Vp and one of the Vp's here will cancel, so we'll end up with Vp square by 3, right? So we're going to get Vp square by 3. And if you have a quick comparison of this average signal power Vp square by 3 with the peak signal power we computed earlier. So you see here the peak signal power is Vp square and the average signal power is Vp square by 3. So that means the average signal power is 1/3 of the peak signal power when the signal is having its voltage or amplitude uniformly distributed in the peak-to-peak range. So we can deduce that from this relationship. So the average signal power is 1/3 of the peak signal power, or conversely we can say that the peak signal power is 3 times the average signal power. So we can now try to represent this average signal power also in terms of delta by using the fact that Vp is Vpp by 2 and then Vpp is L times delta. So we'll use these two relationships to in the average signal power as well, and then get the average signal power also in terms of L and delta. So let's proceed with doing that. So we get the average signal power SA is Vp square divided by 3, but since so that's our relationship. However, since Vp is equal to Vpp by 2 and Vpp is equal to L times delta, we are going to apply both these relations. So in terms of Vpp, we can now write the average signal power. Vp is Vpp by 2, so that will become Vpp by 2 the whole square divided by 3. So that will give it as Vpp square by 2 square, which is 4 by 3. So 4 into 3 will give us 12. So that is Vpp square by 12. And since Vpp is L times delta, so we can replace Vpp by L delta. So that will be L delta square by 12, which gives us L square delta square by 12. So that's 12. All right. So we get the average signal power in terms of the quantization step size delta as L square delta square by 12. So clearly the average signal power is 1/3 of the peak signal power, and in the peak signal power previously we had got this as L square delta squared by 4, right? That's the peak signal power in terms of delta, and the average signal power is going to be 1/3 of it. So that means divide this by 3, so that will give us L squared delta squared by 12. So that is exactly what we have got here. The average signal power is 1/3 of the peak signal power, so that gives us L squared delta squared by 12. And now we can compute the average signal to average quantization noise power ratio. So the average signal to average quantization noise power ratio, we can represent that as SA, that's the average signal power, divided by the average quantization noise power, which is NQ. So that would be L square delta square by 12 divided by NQ is delta square by 12. So we can write that as L square delta square by 12 into 12 by delta square. So obviously we can cancel out this delta, so this delta and this delta square, so the numerator and denominator delta squares will cancel out, the 12 and 12 cancels out, so we end up with simply L square for this ratio. So L square. So what we notice is the average signal power is 1/3 the peak signal power. Therefore, since the quantization noise power has not changed, that remains the same in terms of the expression. So the average signal to noise quantization noise ratio is 1/3 of the peak signal to quantization noise ratio. So let me write the expression we had earlier for the peak signal power to the average quantization noise power, SP by NQ. We had it as 3L squared. So 3L squared, right? So we had this relationship from our previous discussion, and for the average signal to noise power, we are having it as L squared. So we clearly see that the peak signal to quantization noise ratio is 3 times the average signal to noise ratio. This L square is nothing but the average signal to noise ratio. So we can say that the peak signal to quantization noise power ratio is 3 times the average signal to quantization noise power ratio. So using both these expressions, we can now say, so we can make the statement that SP by NQ is equal to 3 times SA by NQ, right? So obviously the peak value is going to be higher than the average value, right? So the peak signal to noise ratio is 3 times the average signal to noise ratio, and this is true when the signal is considered to be uniformly distributed in the peak to peak range. Okay, if it's not uniformly distributed, if it is having some other probability distribution, then this ratio, okay, this factor would change. But for the case where the signal is uniformly distributed in the peak to peak range, we see that the average signal power is 1/3 the peak signal power, or conversely the peak signal power is 3 times the average signal power, and therefore we get this peak signal to noise ratio to be equal to 3 times the average signal to noise ratio. The form of quantization that we have seen till now is called as uniform quantization. Uniform quantization means that the step size is uniform throughout the peak-to-peak range. If you look at the peak-to-peak range, and if you see from the lowest quantization level to the highest quantization level, the step size is uniform in this case. So in this example, the step size is 2 volts. From -7 to -5 is 2 volts. From -5 to -3 is also 2 volts. From -3 to -1, that's 2 volt. -1 to +1 is also 2 volt. So if we see the form of quantization that we have discussed till now, the step size is uniform throughout the range, the peak-to-peak range. So we call this as uniform quantization. So let me write down step size delta is uniform and also fixed, right? The value of the step size is fixed. In this particular example, it is fixed to 2 volts throughout the peak-to-peak range of the signal. Throughout the peak-to-peak range of the signal. Now, a practical consideration is that for practical signals, the quantization error is more sensitive, right? For example, if you're quantizing a speech signal, the quantization error that occurs at lower amplitudes, when the amplitude is smaller, the human ear is more sensitive to that quantization error, and that error gets noticed more obviously than the quantization error that occurs at higher amplitudes. So one of the practical observation is that the quantization error is more sensitive at lower amplitude range. At higher amplitude ranges, it could be the higher positive side or the higher negative side, the quantization error there is not, the effect of the quantization error is not so pronounced or observable. So that is one practical observation. And the second fact is that most practical signals have most components or most part of the signal is concentrated in the lower amplitude region. The higher amplitudes or the higher voltages occur very rarely. So most part of the signal will be dominated in the lower amplitude band or the lower amplitude range. So these two observations then lead us to designing what is called as a non-uniform quantization mechanism, wherein the step size is smaller at the lower amplitude region, and as the amplitude goes up, the step size is made larger and larger. So obviously we don't want to have too many quantization steps because or too many quantization levels, because increasing the number of quantization levels means the number of bits will increase. So therefore we want to kind of balance it in the sense that we want to make sure that the quantization error in the lower amplitude region is small. So we make this quantization step size smaller in the lower amplitude region, and as we move towards higher and higher amplitudes, the step size is made larger and larger, because the higher amplitudes occur very rarely and the sensitivity to the quantization error at higher amplitudes is less pronounced. So therefore we go for non-uniform quantization. So the two practical observations are that practical signals have most of their amplitude components in the lower amplitude region. Okay, and the second observation is that the sensitivity to quantization error is more pronounced at lower amplitudes than at higher amplitudes. Okay, so these two observations make it reasonable to design a quantization system where the quantization step size is small in the lower amplitude region, and as we go higher and higher and higher in the amplitude region, the step size is increased. So if you notice here, the quantization step size, let me mark that. So if you notice here, the quantization step size is very small here, and then it increases, then it's even bigger and so on. So as we go towards the higher amplitudes, the step size is becoming bigger and even bigger and so on. So if you go further up, it will be further bigger, right? So in this particular example, I have marked only say 9 levels, but obviously the number of quantization levels is always a power of 2. So it will be 4 or 8 or 16, 32 and so on. So I have shown you only 9 quantization levels in this diagram for lack of space, but obviously there are going to be another 7 more in this particular case, so to make it 16. So but the concept is that as we go towards higher and higher amplitudes, the step size is made larger and larger. This is called as non-uniform quantization, and the implementation is done by using some logarithmic scale which are called as A law and mu law quantization. So we have what is called as A law, and these are two popular standards used for quantization, and mu law for quantization, that is for non-uniform quantization. Okay, so these are the two important points that we need to realize. We are not going to go into the details of non-uniform quantization in this particular course, but you should still be familiar with the practical considerations. So the two important points here are that the range of most practical signals is such that the signal is mostly concentrated in the lower amplitude region. So as you can see from here, most of the amplitudes are concentrated in this band, in the lower amplitude band. So let me if you see here, most of the signal components lies in this lower amplitude band. The higher amplitudes occur very rarely. If you see the higher voltages, they occur less frequently. So it makes sense that we quantize the lower amplitudes with more number of bits or with less quantization error rather, and the higher amplitudes will have a higher quantization error, but because they occur very infrequently, so their contribution to the average quantization error is small because they occur less frequently, right? And secondly, the perception to quantization error is higher. If there is a quantization error in a lower amplitude region of the signal, that will be felt by the end user in a much stronger way than the same amount of error at a higher amplitude level. So because of this sensitivity to quantization error being higher at higher amplitudes, being higher at lower amplitudes, we quantize the lower amplitudes with a smaller step size as compared to the higher amplitudes. And a couple of very popular non-uniform quantization implementations are what are called as the A law and the mu law, used in different parts of the world, especially for quantization applied to speech signals. Now we will next see our next topic, which is called as pulse code modulation, which is nothing but the process of analog to digital conversion that is specifically used for speech signals, right? Pulse code modulation is a mechanism of converting a continuous analog signal into a digital signal in the form of ones and zeros, and finally representing those ones and zeros as some pulse waveforms. So this entire process is called as pulse code modulation, and we will talk about that in the next part. Pulse code modulation, or PCM, is a technique used to convert an analog continuous waveform into a digital waveform. So It involves the process of sampling, quantization, and encoding, and it converts the analog waveform into a sequence of bits, and those bits are mapped onto another analog waveform or a pulse waveform. So we represent the bits again as some waveform for further processing. So this entire process is called as pulse code modulation, and it is a common method used to convert analog information into digital information and to store that digital information on a disk, or even to transmit that information, right? So we convert the analog signal into bits, which is binary data, and those bits are again mapped to a waveform in the form of pulses. Again, there are many different ways of mapping these bits to pulses, which we will discuss later. Those are called as line codes, and there are different types of line codes, which each having their own advantages and disadvantages, and we will talk about them in the next set of videos. But let us focus today on pulse code modulation, and we will specifically discuss about PCM in the context of voice telephony. When speech is converted to digital, what are the parameters used in pulse code modulation, right? So let's look at the inner blocks within pulse code modulation, which has as the first part, which is the anti-aliasing filter. That would be the first block in a PCM system, and the anti-aliasing filter is nothing but a low-pass filter that will block off all frequencies that are higher than half the sampling rate, because if any signal having a frequency higher than half the sampling rate, then it would cause aliasing. So to avoid aliasing, we want to prevent any higher frequency components from entering the sampling system, so thereby we can prevent aliasing. So a filter which serves for that purpose is called as an anti-aliasing filter, and typically the anti-aliasing filter is a low pass filter, LPF. It's a low pass filter which will have a cutoff frequency. So the cutoff frequency FC for the low pass filter will be around half the sampling rate, Fs by 2. So because of the Nyquist theorem, it says that the sampling frequency should be at least 2 times the maximum frequency present in the signal, and because the sampling system's sampling rate has been fixed, we want to ensure that no frequency higher than half the sampling rate enters the sampler, and for that purpose we use an anti-aliasing filter, which will be a low pass filter with a cutoff frequency around half the sampling rate. Okay, so that is the first part of the PCM system. And then we have the sampler, which will perform the sampling process at some sampling rate. Again, that depends on what is the input signal that is being applied, right? Depending on the nature of the input signal, the sampling system would have its sampling rate fixed accordingly. And then the next part is the quantization, which is the discretization of the amplitude axis. And finally, the encoding part will map each of those discrete amplitude levels onto some binary combination, which will give us the binary data. And also the binary data will get represented as some pulse waveforms. So that would give us the digital output, which would look something like this waveform. So in goes a continuous waveform like this, and at the output of the pulse code modulator or the output of the PCM system, we will get a sequence of pulses that represent our digital data. So that's the pulse code modulation system, which is used in practice for converting analog signals and representing them as digital signals. Now we are going to talk about the PCM system in particular context of voice telephony, right? So in the case of voice telephony, PCM for voice, PCM for that is speech signals. Okay, now human speech signals have frequency components, or if you look at the spectrum of human speech, it's going to look something like this, right? I'm just drawing it roughly. it will be centered on 0, and the f max would be close to around, say, 3.4 kilohertz. Okay, that's the spectrum of human speech. That's the magnitude spectrum. So similarly, that would be minus 3.4 kilohertz. So the frequency range of our speech is typically extending from 0 hertz up to about 3.4 kilohertz. Maybe in some cases it can go up to say 4 kilohertz, and some sounds when we are shouting or speaking in a shrill voice may have higher frequencies, but the normal human speech would typically be have a maximum frequency component of around 3.4 kilohertz. So if f max is 3.4, then the sampling rate that should be used is at least 2 times f max. So 2 times 3.4 will be 6.8, and for PCM in use for speech, the value of fs is 8 kilohertz. So we use fs value as 8 kilohertz in PCM for speech. I'm writing the values here. For speech, it will be 8,000 samples per second, or we write it as 8 kilohertz. So 6.8 is sufficient, but if you recall the analysis, the frequency domain analysis of samples, we need to have gaps between the spectral replicas so that the reconstruction process becomes simpler. So we keep some gap between the spectral replicas. So we use a sampling rate which is more than twice the maximum, okay, rather than exactly equal to the Nyquist rate. We keep some extra margin of around, say, 10%, right? So the sampling rate for speech communication is 8,000 samples per second, and the quantization for speech is done using L equal to 256 quantization levels. So the number of quantization levels used in PCM for speech is 256 levels. That corresponds to N is equal to 8 bits per sample. So that means we are going to sample at 8,000 samples per second. That means for every 1 second of speech signal, we will be taking 8,000 samples, and each of those samples would be represented by 8 bits. So 8,000 into 8 will give us the source bit rate, which is, for every second that we are talking, 64,000 bits would be produced. So the source bit rate for PCM applied to speech signals is 64 kilobits per second, or 64,000 bits per second. So let's write that. So the source bit rate if I just write it as RB, is equal to N times the sampling rate. N is the number of bits per sample, so that will give us 8 into 8,000. So 8 into 8,000, that is 64,000 bits per second, or we can write that as 64 kilobits per second. Okay, that's the practical values used for speech telephony applications. Well, not in the present day, but if you remember, for the landline telephones, maybe a decade back or 15 years back, this was typically the speech source rate that was used for communication on the telephone. But nowadays, with the wireless communications and with the advances in digital technology, we are able to compress these bits and represent this at below 10 kbps. So 64 kbps, one of the advantages of digital communication from the first lecture, if you remember, is that the data can be compressed and represented in a compact way. So that process is called source coding, and in modern day wireless communications, we have the source bit rate reduced to below 10 kbps, and sometimes even as low as, say, 4 kbps is used without degrading the quality of the sound in a significant way, right? So that's the source bit rate for the PCM system is 64 kbps, which is by today's standards quite high. That means for every second that we will talk on the phone, 64,000 bits have to be transmitted to the other side of the communication channel. So that is a huge bandwidth requirement. Okay, but if we reduce this, we can we'll have to transmit less number of bits, or on a given channel we can accommodate more number of users. Okay, so that's the concept of PCM for speech signals. In the next lecture we will discuss in more detail regarding what we call as the PCM word size. That is, how do we decide the number of bits per sample, and hence the number of quantization levels for a given signal, for a given requirement. So what influences the choice of this? Okay, here I gave you an explanation as to why we choose the sampling rate to be 8000 for speech, because speech signals have a bandwidth of about 4 kilohertz, so we use double that, which is 8 kilohertz. And in the next video I will talk about how do we choose the value of L, the number of quantization levels, and hence the value of N, the number of bits per sample, what influences these choices, and we will talk about that. Okay, it's called as the PCM word size. Word size means the number of bits per sample. Okay, we will discuss that in the next video.